So we're very happy to have Joel Tropp joining us from Caltech, where he is the Steele Family Professor of Applied Mathematics. Joel is also a SciAm Fellow and Fellow of IEEE. He's well known for his work in random matrix theory, randomized numerical linear algebra, matrix concentration. And today he's going to tell us something about randomly pivoted Cholesky.
Thank you, Tom. I'm so grateful for the invitation. It's a pleasure to visit. So many people to talk with here. So I have a lot to tell you today. So the first thing I should tell you is that this is joint work with Yifan Chun, who's a postdoc at NYU, Ethan Epperly, who is my student at Caltech, and Rob Weber, who is my postdoc, who is headed to UCSD in the fall for a faculty job. So they did most of the research I'll be telling you about, and they really contributed to both the analysis and the numerical work that made this project so exciting. Okay, but I actually want to tell you about some history first. So, it's fussy. So, Cholesky's method. How many of you have heard of Cholesky's method? Okay, great. That helps. How many of you know who Cholesky was? So, Said. Very good. So Cholesky was French, not Polish, and I'm fairly confident that his name is pronounced Cholesky and not Cholesky or Cholesky or something like that. He was born in Bordeaux in 1875. In 1895, he entered the École Polytechnique, 87th in a class of 223. He studied mathematics with Camille Jordan and physics with Henri Becquerel. So he had some good teachers. In 1897, he entered the School of Artillery and Engineering, very near the top of his class. He was appointed lieutenant in 1899 and entered the 22nd Artillery, where he was sent to Algeria and Tunisia to become a surveyor. So Cholesky spent his entire career as a surveyor. He was interested in taking measurements and making maps. He was detailed to the Army Geographical Service in 1905 with assignments including the triangulation of France, maps of Crete, Algeria, and Tunisia. He married Henriette Brunet, his cousin, in 1907. They had 4 children, not all at once. And in 1910, he wrote a manuscript describing his method, which he may have formulated as early as 1902 during his first time in Algeria. I'll tell you more about that as we go along. In 1914, he was appointed commander of the 23rd Artillery, and he was responsible for commanding this regiment in France. He was sent to Romania for 2 years, from 1916 to 1918, and he was killed in action in France in 1918. And his manuscript was lost. So, what was Cholesky after? So he was a surveyor, and he was interested in making maps. So this is a page from his book, Cours de Topographie, from the 7th edition, 1937. And this is a picture of what a triangulation looks like. So if you want to make a map, you're interested in identifying the location in space of a bunch of points and the angles between them. And so you build some towers so that you can see distant points and take measurements of the distances between these points and the angles between them. Distances are measured relatively more accurately over a longer spatial extent. And so you want to have these long baselines to build up your triangulation. Angles can be measured more accurately, but nevertheless, you have all this information that's inconsistent. Why is it inconsistent? Well, they're measurement errors. The Earth is curved. You have to use spherical trigonometry to work out all of these equations. And so ultimately, to find the locations of all of these points in the map and the angles between them, you wind up with a lot more unknowns than you have equations, and you have to figure out how to resolve that dilemma. And to that end, Cholesky developed a method which he described in this manuscript. Here's a copy of the first page, Sur la résolution numérique des systèmes d'équations linéaires, roughly. Sorry, my pronunciation's terrible. And it's this method that we know today as Cholesky's method. So what did he do? So this is all in modern notation. This is not quite how he explained things. But he was interested in resolving this underdetermined system of linear equations. And to do so, you need to work out an estimate for what the values are, and then each one is corrupted by an error. The estimates come from the fact that, again, there are measurement errors. You have nonlinear equations, which you have to linearize, and also the Earth is not flat. Okay, so U here in this underdetermined least squares problem is the vector of errors, and you want to make the errors as small as possible in L2 norm. Using Lagrange multipliers, you can see that solving this problem is equivalent to solving this linear system, BB transpose X equals F, and the variable, the errors you're interested in, takes the form B transpose X. Okay, so this is one of the forms of the normal equations. Now, when you look at this equation here, you can see that the matrix BB transpose, which I'll now write as A, is positive semi-definite because it's an outer product. And Cholesky was interested in finding methods for solving this type of linear system. Okay, so given the data you collect, you can reach this point. Now, his idea, which is related to Gaussian elimination, is to factorize A as a product of a lower triangular matrix and its transpose, LL transpose. This is not the way he would have expressed this at the time. The reason that this is valuable is that once you have this factorization, you can solve the linear system from the normal equations in two steps. First, you solve the equation Ly equal to F, and then you solve the second equation L transpose X equal to Y, and that gives you the solution X, and therefore the vector of errors, which allows you to correct your measurements. The reason that triangular systems are so powerful is that you can solve them one equation at a time. So you see that you can find the first entry of the vector Y just by dividing through by the diagonal entry of the triangular matrix. Once you know that, you can find the second entry of the vector Y from the second equation, because there's only one unknown remaining, and you can pass through the equations one after the next. So this is what we all learn in numerical linear algebra. Okay, so the real question is how we produce this factorization. And this was Cholesky's idea, how we obtain this factorization of this matrix A. So the way that I like to think about this is different from the way that Cholesky approached the problem. So one way to think about reducing a matrix to lower triangular form is to try and eliminate the columns one at a time. Okay? And so the basic idea behind the method is that if you have a positive semi-definite matrix, you can decompose it into two pieces by pulling off the first column and forming its outer product, and then normalizing it by the diagonal entry. So this matrix is obviously positive semi-definite, because it's an outer product of the same vector with itself. And this matrix happens to kill off the first row and column of the matrix that you started with. And you can check, it's an exercise, that the block here in the corner, which is called a shear complement, remains a positive semi-definite matrix. Okay, this is great. We've removed the first column, we have another PSD matrix, and so we can iterate. Okay, so Cholesky's method in the outer product form splits off the first column of the matrix into a rank 1 term, and then we've zeroed out the first row and column, and we have a residual A1. Now, we're going to eliminate the second column, which has a 0 up top, and so looks like this. We can peel off that rank 1 factor and add it to our approximation to obtain a 2-column positive semi-definite approximation, another residual, which now has zeros in the first 2 rows and columns, and so forth. So at each step, the residual is getting smaller and smaller, and we just keep peeling off one column at a time and putting them into the approximation, and then when we run out of matrix here, we have a lower triangular factor times its transpose. Okay, I hope this is familiar. It's hard to understand all of this at this rate of presentation. As a quick note, I'll say that the triangular factor after t steps consists of these vectors L1 up to LT that we've been peeling off using this process. And the residual is the initial matrix minus the current triangular factors. Okay, great. So this is not what Cholesky did. He did something a little bit different. He said, why don't we generate the columns of this residual matrix on the fly? So now the way he formulated his approach is to start with a factor matrix L, which is empty. At step T, I'm going to pick off the teeth column of the residual. So I pull off the teeth column of A. I find the teeth column of the approximation, subtract it off. I normalize it by the square root of the diagonal entry. That corresponds to the normalization here. So I've split it into two pieces, one on each part. And then, whoops, sorry, it's fussy. And then I take this column that I found and put it onto the factor and I repeat. So this is essentially the method that he proposed, and the key idea here in his approach is that we don't actually update the matrix. At each step, we only pick off the new columns one at a time. The reason this is important for Cholesky is that he's calculating by hand. He doesn't want to have to subtract off this outer product from his matrix every single time, because that would involve erasing all of the numbers and overwriting them with new numbers. So it's interesting to realize that a lot of numerical analysis was developed by people who were making calculations on pieces of paper by hand. And for them, the way that we organize the operations is extremely important, and they're very concerned about the number and type of arithmetic operations they have to perform, because they got to do them themselves. Okay? And up to the organization of these calculations is exactly what Cholesky proposed. And the reason was that his computer looked like this. This is called a dactyl adding machine, calculating machine, and it was able to perform this product, sum, accumulate, divide operation in one step. And so his algorithm was designed explicitly to take advantage of the strengths of this machine that he had. And he reports that using this machine, you can solve a system of 10 equations in 4 to 5 hours. And he also says that during his work on the triangulation of Algeria, he solved 56 equations using this approach. So that's about 30,000 operations. Okay. Just for the factorization, not speaking of the triangular solves or forming the matrix A. Okay, so that was his work, and the thing I want to emphasize is that the design of his method was really adapted to his computational platform. It addressed a pressing problem of the time, which was to make accurate maps. Now, it turns out that Cholesky was maybe not the first person to realize that you could factorize a matrix into LL transpose. This appears in a work of Otto Toeplitz from 1905, but his approach wasn't algorithmic. Cholesky prepared this manuscript describing the method in 1910, and he died in 1918. And the method would have been lost, except that his colleague, the Commandant Benoit, publishes his approach in this paper. This is the title, not the abstract. Note on a method of solving normal equations coming from an application of the method of least squares to a system of linear equations whose number is smaller than the number of unknowns, process of Commander Cholesky, published in the Geodesic Bulletin in 1924, so 100 years ago now. Now, the method was lost again. It was rediscovered by a Polish mathematician named Banakiewicz in 1938. It was discovered again in the United States in 1944 by a mathematician in Michigan named Dwyer. And he's the first person to recognize that it was a matrix factorization. Now, in 1944, a Danish mathematician named Henry Jensen surveys methods for solving the normal equations, including Cholesky's, and says that Cholesky's method seems to have all advantages. His work was described in Math Reviews, which was in its 7th volume, so it was very easy to read all of the Math Reviews and find what you're looking for. And John Todd came across this survey when he was preparing to teach a class on numerical computation at King's College London in 1946, after the war. He said he didn't know anything about solving a linear system, so he had to go to the literature. And he's really the one that in the UK rescued Cholesky's method from obscurity. And he had in his class Leslie Fox, who's a well-known numerical analyst who worked with Wilkinson and Turing to develop Cholesky's method. And it was analyzed for the first time by von Neumann and Goldstein in 1947 in what's been described as the very first numerical analysis paper. So they showed that Cholesky's method with pivoting is stable in floating point arithmetic. They described it as matrix factorization and invent most of the basic notions in numerical analysis, including conditioning and backward stability in this work. In the 1960s, Cholesky's method had already become textbook material. It appeared in at least these 3 books. And at present, it's still the standard algorithm for solving small, dense linear systems. Okay, so that's the preamble. All right. Normally, I'd ask if there are any questions, but I want to press on. So I hope that, aside from the history, this method is familiar to all of you from your numerical linear algebra courses. Ooh. All right, so I want to tell you about a different thing that you can do with Cholesky's method, which has been known for a long time, but perhaps was not as widely appreciated, and that's something called column approximation. So let me tell you about column approximation. So let's revisit the basic step in Cholesky's method. So remember, we have a positive semi-definite matrix, which we're going to split into an approximation and a residual. And we're going to proceed iteratively, transferring information from the residual into the approximation at each step. And the approximation is always going to have this form of an outer product. So we are not only approximating the matrix, but we're producing structure as we do this. Okay? And that structure helped us solve linear systems before. It's perhaps valuable in and of itself, though, having this approximation of the matrix. Okay. Now, one thing you might have noticed is that when we implement this method, we need to divide by the diagonal entry A. Are the diagonal entries of a positive semi-definite matrix strictly positive? Not necessarily. So 0 is a positive semi-definite matrix whose diagonal entries are 0, so you might have a problem implementing this approach. So what do you do to avoid division by 0? You need to pick a column to eliminate where the diagonal entry is not 0. Okay, so this is called pivoting. And it's also possible that even with pivoting, where we pick a column with a non-zero diagonal to eliminate, we might still run out of matrix. Okay, so imagine the matrix were rank 1. After one step, there's nothing left. So in that case, you need to stop the algorithm early. And that leads to a formulation of the algorithm that looks something like this. It's called pivoted partial Cholesky. And the idea is the following. We're going to start with the initial residual equal to the input matrix A, and our initial approximation is going to be 0. Okay? So the approximation is this outer product here. And at each step, we are going to pick a column to eliminate from the matrix. So we're going to zero out the row and column indexed by ST. To the approximation, we are going to add the outer product of the ST column of the current residual divided by the ST diagonal entry of the residual. So we're adding it to the approximation. We're removing it from the residual. So we're transferring this information from here to here. And then we're just going to proceed until we get bored and we stop. And the output will be an approximation, A hat should be A hat K, and the columns that we decided to eliminate from the matrix. All right, good. So let's see what this looks like in practice. So here is a PSD matrix associated with a clustering problem. So I've got 3 red data points, which are kind of close to each other, and 3 blue data points, which are kind of close to each other. And the matrix I'm going to form is a Gaussian kernel matrix that reflects the distance between each squared a pair of data points on a scale of about a little bit more than 1. Okay, that's sort of the size of the cluster. All right, so it is a beautiful fact that this matrix is always positive definite, regardless of the choice of data points. And you can see that the red points, when they're organized this way, all make a nice big diagonal block. The blue points all make a nice big diagonal block together. All right, so we'd like to apply Cholesky's method to this matrix and see what happens. We want to see what the approximation looks like. So let's do that. Why not eliminate the second column? We can eliminate whatever column we want, and that's the one I happen to pick. So we've taken the second column out of the matrix. Here is the approximation obtained by that column divided by the diagonal entry times the the transpose of that column. We've zeroed out that column in the matrix to obtain this residual, and you can see that that column already explains the other 2 red points pretty well. The first 2 red columns are almost gone now. So just eliminating that column already explained a lot. You can see that it didn't do much to explain the blue columns. So let's eliminate another column. As it happens, we will eliminate the third column, being a little bit arbitrary, but we remove that column from the residual. We add it to the approximation. We divide by the associated diagonal entry, and we update the residual. And so now we can see that this blue point has explained the other 2 blue points pretty well. And so there's really not a lot of matrix left to approximate. So even though we've only eliminated 2 columns, there's not a whole lot left. That makes sense? So we can see that this process of running Cholesky's factorization method just for 2 steps has already produced an excellent approximation of this 6x6 matrix. And there's not a lot left. Now, the other thing I would like you to note is that the diagonal entries are telling us something, right? So you can see that this red point has explained this red point quite well, and it's explained this red point a little less well, but these numbers are both pretty small. And so this sort of signals that there's not a lot going on in the first 2 columns. You can see, however, that the diagonal entries here are a bit bigger because this blue point does an inferior job expressing these 2 points. And so the diagonal entries are really providing us some information about what still remains for us to approximate. Okay, we're going to take advantage of this insight in just a moment. Okay, so in summary, Cholesky's method with pivoting can be used to approximate a matrix. We don't have to run it all the way for it to do something useful. And the diagonal entries of the matrix provide us some evidence about what remains to do. So you can see here after the first step that these entries are still quite big, which warns us that we have some work to accomplish. All right, so you might wonder now, what kind of approximation do we reproduce by this process? So the method goes all the way back to the literature on integral equations from 1930. It's called the Nystrom approximation. In the discrete case, we let A be a PSD matrix and we let S be a set of column indices. The Nystrom approximation of A with respect to the columns in S is the matrix obtained by pulling out the columns of A listed in S and the corresponding rows listed in S, which are transposes of each other, because the matrix is positive semi-definite. And then I take the principal submatrix indexed by S and take its pseudo-inverse, and I jam that in the middle. So you can see that this is an approximation we can produce if we only know the columns of A listed in the set S. Okay, so this is called a Nystrom approximation. Does this look familiar? Yeah, it's the other part of the Schur complement, right? This thing that we got by running Cholesky's method. And indeed, it is exactly the thing that you need to remove from the matrix to get the Schur complement. So this approximation is actually a very beautiful object, which is maybe not surprising once you realize the connection with Schur complements. It has the property that the range of the approximation here is the same as the range of the columns that we picked out. This is pretty easy to see because the range of this whole matrix has got to be a subset of the range of these columns, and this is a matrix that's lined up the same way. So the rank doesn't get smaller. The approximation A hat S of this form and the residual, which is called the Schur complement with respect to S, are both positive semi-definite matrices. So it's obvious that this is positive semi-definite. It's less obvious that the Schur complement is positive semi-definite, but this tells you that somehow this is a very natural thing to do. And moreover, this is the maximal approximation of the matrix A, whose range agrees with these distinguished columns and that has these two properties. So this is a very, very fundamental construction. All right. Now, what's remarkable is that the Cholesky method produces a Nystrom approximation. So if you pick pivots S1 up to Sk in any order and collect them in a set S, that the output of the pivoted partial Cholesky method is exactly this Nystrom approximation, again, regardless of the order of elimination. So this is a interesting result that is not trivial to prove, but it tells you that Cholesky's method isn't just doing something ad hoc, even though that's the way it might appear at first. Rather, it's producing an approximation with a very strong optimality property. Okay. Now, once you realize that Cholesky's method is producing this remarkable approximation, you might ask, how is it that I can select columns, select pivots, to maximize the approximation quality? So that's the next idea. So our goal then is going to be to select a pivot set S to attain the highest approximation quality that we can. Okay. This idea Stewart says this idea goes back to Lawson and Hanson's book on least squares in 1974. I could not find this in Lawson and Hanson's book, so it seems possible that he did not check his sources. This is just to suggest that the idea of using Cholesky's method to produce a matrix approximation is already quite established. Okay, so we're going to measure the approximation error in the trace norm. So the trace of the matrix A minus the approximation, which is equivalent to the trace of the residual. And because these are both positive semi-definite matrices, the trace has to be positive. So it's a reasonable way to measure the error. Now, our goal at the next step is to eliminate a column to reduce the trace error the most. And the idea, based on our numerical experiment on the previous slides, is going to be to use the diagonal entries of the residual AT as a guide to which columns are going to help us out the most. Make sense? All right, we saw that a big diagonal entry seems to signal a column that still has a lot of information in it. Okay, and the reason we're going to do it this way instead of working harder is because it's really cheap to look at the diagonal. We'll come back to this point later. Okay, so there's another justification which is a little more mathematical. This justification already appeared in von Neumann and Goldstein's paper on Gaussian elimination. For a positive semi-definite matrix M, the diagonal entries are non-negative and they control the off-diagonal entries in this sense. So the square of an off-diagonal entry is bounded by the product of the corresponding diagonal entries. That's true for all I and j. So if a diagonal entry is small, it's guaranteed that all the other entries in the column are small, and that column isn't going to do much for us. Okay? On the other hand, if mjj is large, it's possible that the entries in that column are large, and that might be a good column to look at. But there's an asymmetry here. Small diagonal entries definitely tell us that we don't have to worry about that column. Big diagonal entries might or might not help. It could be the entire column is 0 except for the diagonal, right? Okay, so we're going to use this intuition as a method for developing strategies for selecting columns. All right, so let's plow forward. So the oldest approach to column selection based on the diagonal entries is called greedy pivoting. Von Neumann and Goldstein called this pivoting for size, and it's also called complete pivoting for reasons that I want to elaborate on. And their strategy is simply to say that if the diagonal entries are useful, I want the biggest one I can get my hands on. So at each step of the Cholesky decomposition process, I am going to look at the diagonal entries of the residual, and I'm going to find the index S where the maximum entry appears on the diagonal, and that's the column I'm going to eliminate. All right. So this is, in the parlance of machine learning, a method that exploits the information that we have maximally. It says I'm going to go for the biggest entry on the diagonal every time, but it gets distracted by shiny objects. It's like, you go to the reception later and you're like, oh, that bowl of chips looks good. I'm going to keep eating chips. Chip, 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 chip. All right. And then you forget that you're going out to dinner afterward, where you're going to get something much more delightful. So this is what the greedy method does. It just keeps grabbing the thing that's right in front of it without any further contemplation. So you might ask, maybe there are better ways to do this. Any thoughts about better ways? Okay, so the word random appears in the title. So you might imagine, all right, let's do something randomly. So in the machine learning literature around 2000, there was already a proposal to do something else, to produce column Nystrom approximations, and that's to sample each of the pivots uniformly at random. So at each step, I'm just going to pick a random column and eliminate it. Okay, this is a pure exploration. You're like, you don't learn anything or experience. You're just like, okay. Now, the intuition from machine learning is that data are IID, right? It's not true. So the intuition is that data are IID, and therefore one data point's as good as any other, so you might as well just pick random data points. Now, the reason that this is not a valid intuition is simply because once you have modeled some of the data, there is stuff you've already learned about that you don't need to model again. And by picking things at random over and over again, you just don't learn from your experience, okay? And so that's not what you want to do either. Okay, so what else might you do? Well, we want some combination of these strategies, the area mediocritas. This is what we call random pivoting. It's a method of importance sampling, where we take seriously the idea that the diagonal has information in it, but that information is imperfect. So instead of picking the biggest diagonal entry, or just one at random, we're going to sample a column in proportion to the size of the diagonal entries of the current residual. So this is the matrix we still need to approximate. We'll make a probability distribution out of the non-negative entries of its diagonal, and we'll just sample a column from that distribution. So it takes seriously the idea that small columns are not informative, but at the same time, big diagonal entries might or might not be helpful. Okay? So it allows us to balance exploitation and exploration to hopefully produce a better approximation. So this idea does appear in the literature, but the provenance is thin and it's fallowed. No one does this. And yet it is shockingly effective. The reason people apparently did not know this is because no one implemented it. Okay, so sometimes you get the idea that that mathematical theory tells you everything, and this is not really true when you're studying numerical algorithms. It might be that the performance of the method is not adequately described by your intellectual approach. Okay, one other quick comment before we continue. I want to talk about what this method does and show you some examples. It turns out these methods are actually all part of a family of examples, which is called Gibbs pivoting. So you could also imagine sampling a new column to eliminate in proportion to a power of the diagonal entries. Power beta is called the inverse temperature. Random pivoting is the case where beta equals 1. Not too hot, not too cold. Uniform pivoting is the case beta equals 0, so infinite temperature. And greedy is the limit as beta goes to infinity, so the 0 temperature limit. So these are all part of a family of strategies. Part of what's interesting, which I'm not going to prove to you, is that greedy pivoting and uniform pivoting actually fail catastrophically for some examples, whereas somehow this intermediate temperature allows you to prove theorems in addition to working in practice. Okay, so let me give you some intuition about why this is a sensible thing to do. So, what's the intuition behind this algorithm? The idea is that it makes progress in reducing the residual matrix on average. And you can quantify very cleanly how much progress you've made using the law of total expectation, a very deep fact from discrete probability. So what are we going to do? Imagine that we start this procedure at the matrix A and we take one step to produce a residual A1. What is the expectation of the new residual after one step? Well, that is the sum of the value of the residual, if I eliminate the sth column, times the probability of eliminating the sth column. So I said that the probability is proportional to the diagonal entries, which sum up to the trace. And here is the residual. We take the initial matrix, we remove the outer product of that column and divide by the associated diagonal entry. Okay, this is a probability distribution, so this is an average, and so it just spits out the initial matrix A. The diagonal entries cancel. That's why this is a good distribution. And all that's left then is A minus 1 over the trace of A times the sum of these outer products, which is also known as A squared. Okay, so in short, we can write down an explicit formula for the expected residual after one step of this process. And it has this very elegant form, tells us that we remove A squared over the trace of A. Now, to understand what's happening here, let's take the trace, which is going to be our measure of error. Okay, so the trace of the residual on average is equal to the trace of the thing we started with times a damping factor. So we've attenuated the trace by performing one step of this procedure. By how much? Well, 1 minus the trace of A squared divided by the trace of A quantity squared. Okay, how do we understand this? Well, this is always between 0 and 1, so that's a good sign. And when is this big? It's big when some of the eigenvalues are a lot bigger than the others. Okay, so when the eigenvalues are spiky, the trace of the square is a lot bigger than the square of the trace because some of these guys get amplified a lot before we add them up. Okay? So there's a large improvement when the eigenvalues are spiky, which is to say we make progress in reducing the residual when the residual still has a low rank approximation. Okay? That's why this algorithm works. So long as there's something to find, we're going to find it on average. If we mess up, doesn't matter, we get another shot. Okay? So that's roughly why this method is effective. And we can prove the following theorem, which turns out to be quite hard, but is ultimately based on this intuition. So the idea is that we'd like to compare the approximation that this random pivoting method produces after k steps with the optimal approximation of some form. So we're going to let bracket AR be a best rank R approximation of A in the trace norm. Okay, and we're going to compare our error from this algorithm with the optimal error. And so our goal is to get within a 1 plus epsilon factor of optimal, but we're allowed to use more columns than the optimal rank we're comparing with. Okay, so K certainly couldn't be smaller, but our hope is that it's not going to be a lot bigger. Okay, so we define the dynamic range of the approximation to be the error in the rank R approximation divided by the trace. So this is how far we have to push the error down to get from the initial trace to the optimal value. So how much do we have to reduce the error? And the claim is that if we take r over epsilon steps plus some log factor, we will obtain an approximation that is competitive with the best rank R approximation. Okay. So roughly speaking, you should think about epsilon equal to 1. So to get within a factor 2 of the best rank R approximation, we need R columns plus R times a logarithm. I like to think of this logarithm as being smaller than 37, which is the logarithm of the machine precision, because you couldn't possibly push the error farther down than that. Okay, so you should think about this as a constant times R. Okay. Now, no similar result can possibly hold for greedy pivoting or uniform pivoting because there are examples that flame out. Again, greedy gets distracted by shiny objects. Uniform can't take advantage of what it's learned. And it's also worth noting that there are matrices for which a Nystrom approximation that satisfies this bound requires at least R over epsilon columns, so you can't really do much better than this. It's just a question about how parasitic this log factor is. Okay. And again, this reflects sort of a geometric improvement at each step. Okay, let me pause and ask if there are any questions about this theorem or how this is connected with column approximation or anything else. Yeah.
Why not consider this for a sort of general inverse temperature? Like you have this sort of zero temperature, temperature.
Yeah.
You might expect maybe there's some phase transition or critical value temperature in beta. Why not try general beta?
So we have not tried general temperatures. You certainly could, and it seems entirely plausible that that will work better sometimes. This theorem is based on an argument that seems to require temperature 1, because you could see that in the estimate there's a cancellation between this first power here and this diagonal entry, which appears in the Cholesky update. So in some ways, the temperature 1 is really tuned to the structure of the Cholesky update. As you say, in practice, something else might well work better. But honestly, we don't know. And we have no idea how to analyze it either. Yeah. More questions? Hey, Mariam.
What is the worst case matrix?
For which?
For the R over epsilon.
I can't remember.
No insight from
I can't remember what happens. I mean, like, it's one of these things where you probably cook up like a diagonal block and then some other diagonal blocks, and what happens is that you really have to pick columns from each of the blocks to approximate the matrix. That's usually the way these things go, but I don't remember. Yeah.
Yes, I'm motivated by the contradistinction between greedy algorithm and the random. There must be a class of matrices which we guess we can call convex. Your greedy will guarantee the best. What is that class of matrix?
I don't know. So our experience is that greedy sometimes is the best method, but rarely.
Because this problem definitely is very far away from being a convex problem in some sense. I guess I'm just wondering what is that convexity?
Yeah, I don't know. In short. All right. Anything else before we go on? Okay. So far, this has all been pretty abstract. What I'd like to emphasize from this section is that Cholesky's method was proposed as a method for solving positive semi-definite linear systems that arise in geodesy. What I've shown you is you can also use Cholesky's method to produce low-rank matrix approximations, but I haven't explained to you why you might want to do that or what the advantages of this method might be as opposed to something more sophisticated. So before I continue, let me just give you a little bit of pseudocode to show how this algorithm works. So it's pretty similar to the method Cholesky devised in the first place. We need to keep track of the diagonal of the matrix, and at each step we sample a column proportional to the diagonal entries of the current residual. We pull out that column, generating it on the fly. We normalize it. We add the column to our approximation, and we update the diagonal to reflect that new column, okay? So this is really cheap, okay? So in particular, the only access we make to the initial matrix A is reading off its diagonal at the first step, and then reading off the column that we're adding to the approximation, and that's it. We don't even look at the whole matrix, which seems surprising. How can you approximate something when you don't look at it? Nevertheless, it is possible. And the outcome is that you can run this algorithm looking at k plus 1 n entries of the matrix, using kn storage for this factor, and using k squared n arithmetic. So it's a very inexpensive algorithm when the rank of the approximation k is small compared with the dimension of the matrix. You should be thinking about very big matrices and small to medium rank. Okay, why is this useful? So now, even at this late moment, we are going to go in a different direction, and I'm going to tell you a little bit about kernel methods. So what is a kernel matrix? A kernel matrix is a way of measuring similarity between data points. So the kernel takes as input 2 data points and spits out a number that tells us whether or not they are similar. And we say that it's positive definite if the matrix that tabulates the pairwise similarities of a data set is always positive semi-definite. This seems like a strong requirement, and yet there are tons of kernels that have this property. One of them is the inner product, where the kernel matrix is the Graham matrix. Another example is that Gaussian kernel that I showed you before that measures the square distance between data points and then runs it through a Gaussian function. Okay, the remarkable idea, which is called the kernel trick, is that any algorithm that you design for one positive semi-definite kernel, positive definite kernel can be implemented with another positive definite kernel without any revision. And so in particular, algorithms involving Graham matrices are associated with this inner product kernel, and these algorithms can also be implemented for other similarity measures like the Gaussian kernel without any change. This is the idea behind kernel methods. They convert nonlinear data analysis into linear algebra. We're pretty good at solving linear algebra problems. Okay, so these methods were wildly popular in the 2000s before they were overrun by neural networks. They're still prominent in scientific machine learning because they're interpretable and they're pretty reliable. Now, there are all sorts of kernel methods. You can use them for regression and interpolation. You can use them for clustering. You can use them for finding nonlinear features in data. What's the problem? It's the scaling. These methods are very hard to implement for large data sets for 2 reasons. First of all, to make that kernel matrix, which tabulates pairwise similarities, you have to compute the kernel at each pair of data points. So that requires about n squared evaluations. It's very expensive. You have to write that matrix down. So imagine if you have 1 million data points. Oh, that matrix requires 1 trillion numbers to store. Okay, so this is bad news. Furthermore, the linear algebra is expensive. How much does it cost to solve a dense linear algebra problem of dimension n? Up to n cubed operations. So this is deadly. And this is one of the reasons that kernel methods were not as widely adopted as one might hope. It's because they're simply hard to implement for large data sets. But there's an opportunity, which has been noted as far back as 2000, which is that kernel matrices often have rapidly decaying eigenvalues, so you can approximate them by low-rank matrices. All right, so how might you do that? Well, you could use this algorithm I just showed you, Cholesky's method with random pivoting, which adaptively picks k data points as landmarks and uses those landmarks to approximate the entire kernel matrix. This is great because you only need to look at k columns of that matrix plus the diagonal, so it's cheap. You don't need to compute all of those similarities between all the data points. You don't need to store the whole matrix. You only need to store the columns you picked out. And moreover, solving these linear algebra problems with this low-rank matrix, which you've presented as a factorization, only costs k squared n operations instead of n cubed. So think about k as 100, even if n is 100,000 or 1 million. All right, so there's a huge benefit here. And this algorithm somehow provides guarantees on the quality of approximation and allows you to scale these kernel methods to larger data sets. So I'll show you an example and then we'll wrap up. So one fundamental application of kernel methods is spectral clustering. It's similar to the example I showed you before. You're trying to take some data points and figure out which ones are attached to each other. This involves historically making a kernel matrix, finding its row sums, computing some eigenvectors, applying k-means, and the costs, as I said, are quite high. A natural approach to solving this problem faster is simply to approximate the kernel matrix using this modern adaptation of Cholesky's method and perform the same algorithm on this low-rank matrix. Okay? So it's much cheaper. And let me show you an application in molecular dynamics. So the task is to identify metastable states of alanine dipeptide molecules. Okay, so biological proteins have different conformations. They like move around. This protein has 3 different arms which move in different directions, like I don't know, safety dance or something. And your goal is to figure out what these different conformations are because they identify biological function. So one way you could get at this is by writing down the positions of the atoms in these molecules and simulating how the molecules evolve. And so you can collect 250,000 trajectory points which describe how these molecules are bunking around. Okay, you can apply spectral clustering to this method and plot the results. So you can see that there are 1, 2, 3, 4 metastable states here, which are visible in this plot. And these are the states that are identified by using this randomly pivoted Cholesky method to produce a spectral clustering. Okay. In contrast, if you use uniform pivoting to produce a clustering, it makes a lot of mistakes. It picks landmark points all over the place. It gets confused about whether points here in this cluster and that cluster, and in fact assigns them to something completely different. The greedy method also gets confused about the points here in the corner of this cluster because it really is going gung-ho on the points here without really paying attention to the parts of the matrix that still need approximating, like this and this. So it doesn't do such a great job. Part of what's interesting about this example is that the prior art in the biochemistry literature for solving this problem is to subsample the data because there's too much of it, and to run this algorithm for about 30 hours on a workstation. If you use this landmarking approach using this modern version of Cholesky's method, you can solve the problem with all the data. You can use 150 landmarks, which is enough to match the reference clustering that you get if you really work at it, and it takes 10 seconds on a laptop. Okay, so this is a factor of 3 million difference over what was reported in the biochemistry literature. Now, it should be said that they were not using even what they should have been doing, which is one of the reasons we need computer scientists and applied mathematicians. But nevertheless, there is a huge advance, and we still obtain scientifically valuable results. And just to give you some idea about how these different pivoting methods compare with each other, here is the, good Lord. Here is the rate of misclassification for different methods as a function of the number of landmark points, the number of columns we use to approximate the matrix. So you can see that this random pivoting strategy produces excellent approximations that drive the misclassification rate down exponentially fast. Okay, so by the time you've taken 200 landmarks, you're only misclassifying 1 point in 1,000 as compared with the reference. The other methods either get confused and produce worse results or never produce anything useful at all. Okay. So the fact that this algorithm actually produces guaranteed approximations is borne out in the numerical experiments. All right, so let me summarize. Cholesky developed his method to solve least squares problems arising in geodesy, and his goal was really to exploit the strengths of the computer that he was using, this Ductile calculating machine. It became the standard method for solving positive semi-definite systems, and later people realized that you could use Cholesky's method to produce low-rank approximations of matrices, but this doesn't seem to have been widely known. In fact, it really only appears in one of the linear algebra textbooks that I could find. I think because there are other methods that are better. Around 2000, machine learning researchers realized that Cholesky's method had a powerful role to play in implementing large-scale kernel methods. They studied uniform pivoting and greedy pivoting in that context. And we realized that using a little bit of insight from randomized linear algebra, we could produce a better pivoting method, which has a rigorous analysis and seems to produce much better matrix approximations in practice. And what's really important about the modified algorithm is it really addresses the challenges of large-scale kernel methods. We don't even need to look at the whole kernel matrix to be able to produce these approximations, which is critical for scaling this to larger problems. And so the tagline, which I would like to conclude with, is that good algorithms have a very long lifespan and they can be adapted to new computational settings. Cholesky's method really is a cornerstone of numerical mathematics, and we were excited to see that it seems to have a new role to play even 100 years after it was first published. In other words, la plus ça change, la plus la même chose. Thank you.
Questions?
Yeah, Kevin.
As a randomized algorithm, some are going to be better than others.
Yeah.
What's the variance look like on this algorithm? And can you exploit that to do it multiple times and pick the best one?
Yeah, so you're better off just running it longer and then compressing the results. So there are ways to reduce the number of columns you use from a larger sample. These algorithms tend not to be very variable because they're martingale-like approaches. They're super martingales, really. So even if you make a mistake, you fix it later. So it has a bit of a different character from like Monte Carlo methods where the variability is very high. So even though each particular random column selection might not be great in the aggregate, if you make a mistake, you will fix it. And we didn't actually prove any probability bounds, but you can probably show that there is an exponentially small probability of doing like a factor of 2 worse or something. Yeah. Yeah, Alex.
Presumably, you could imagine like, a really expensive algorithm that could do better in which, maybe you look at the whole matrix in every iteration, right? And take the pivot that has the biggest column norm.
Yes.
Right, and that's like the true greedy algorithm.
Yes.
Because that minimizes the next.
You could.
Error, right? Like, how does that? Do you know like how that compares to like? Because that's like another measure of suboptimality.
Yeah.
Is that even good?
Yeah. So some people do that. It's too expensive to run for kernel methods, which is why we do not do this. My sense is it actually works reasonably well, but I actually don't know of a proof that's better than just saying like use Nemhauser to argue that greedy algorithms are nearly optimal for submodular problems. Yeah. Yeah.
How would you compare the results of this method to something like the random rangefinder method or sampling by ridge lever scores?
Okay, ridge lever scores are a disaster. In fact, you can see that on this plot here where they accomplish nothing. Lever scores are a bad idea. Not always, but most of the time. So I don't want to start ranting about this, but the proof is in the picture. Now, what about the randomized rangefinder? It works better than this, but you can't implement it for a kernel matrix because it requires multiplication of the matrix by a random vector, which requires you to produce the entire matrix. So there are situations where you can do that, but for large-scale kernel problems, it's not a great plan. So really, if you could do that, that's what I would recommend. In this case, I don't think that you can scale that method even to the problem I've showed you. So, yeah, please.
This may be a little bit of a philosophical question, but you don't have a, I guess I'm thinking of, so you have a random algorithm to solve this problem that's obviously really hard and sort of complex. But in terms of your exploration, do you have a sense of, I guess, which one is it? So could there be a deterministic algorithm that does, I mean, just as well as this
Yeah.
random algorithm at finding sort of the optimal way to do the pivoting and, the signature of what
Yeah.
you're seeing
Yeah.
for the randomness is just, you can't
Yeah.
get to it.
Yeah, so there are algorithms which are guaranteed to produce near optimal column choices. There's one called rank revealing Cholesky, which was published by Gu and Moranian in 2004. These algorithms are not so suitable for kernel matrices because they require you to swap columns in and out in an effort to maximize the determinant of that principal submatrix you're pulling out. They're very beautiful and they have very, very strong guarantees, but they're also very expensive. So somehow this seems to be, in fact, we were planning to use determinantal point processes or something fancy, and we just kind of got stuck because this worked so well. But I am certain that there are algorithms that have better theoretical guarantees, and whether or not those are borne out in practice is not so clear. This is the best thing we've found so far. Yeah.
Okay.
Thank you so much.